Okay, so this is where we left off with yesterday. So we've dealt with three subatomic particles. Okay, now when we talk about an atom, okay, it has these three subatomic particles because atom is even smaller than that of an element. Now, an element is a pure substance. And as we look over here, according to this chart, which was copyrighted in 1991, okay, okay, so this was probably, what do I want to, I wouldn't say state of the art. It still does the job, okay? And the reason I say it that way is because it really has not changed that much. There may be some more elements down here in this lower D and F block, but for the most part, those are all synthetic or man-made elements. That's why you see in black, all of those elements are metals. Okay? If it's written in red, it is a gas. If it's written in blue, it's a liquid. And if it is clear, like what we see in the bottom of the F block and element 43, which is technetium, those are all synthetic or man-made elements. So that's why those letters are clear. So what we see happening on this periodic table, going from left to right, we go from metallic characteristics to those that are maybe ambidextrous. That would be a good way of looking at it. Is anyone in? You would know if you are ambidextrous. Yeah, you are coordinated enough in both being, in your case, left and right. Okay? One of the things, maybe you got to think fast. How many of you can, and I think it would be pretty high, when you're looking at a mirror image, that's one of the things you always got to think about. Always say left, over here. But for me, that's my right arm that does that. Can you think that quick? And a lot of you probably can. There's really no reason with a lot of practice that you can't. And you might laugh at this, but it does happen. Let's say someone is scheduled for surgery to remove their left kidney. So what happens is they may, unfortunately, remove the wrong one. It happens. Okay? So, and with that just comes a lot of practice. Okay? So the reason we say ambidextrous is because metalloids, I did replace the battery in here, so now I got a better laser sight. I don't think it really shows it on your table. It does not. But again, for those of you sitting over there, okay, this line right here, it's a zigzag line that starts between boron and aluminum. And see there's a red line there that zigzags? Okay, so the zigzag line there. All elements that touch that zigzagged line are what we call metalloids, with the exception of aluminum. Okay? The reason we call them metalloids is because they have metallic-like characteristics and non-metallic-like characteristics. So they can kind of do both. That's why we said some of you may be ambidextrous. You can do writing with your left hand or writing with your right hand. So those are kind of haven't decided what they really want to do yet. So again, they're metalloids. Then those that are to the far right, of course, are non-metals. Now, when you look at this, you might be thinking, well, if hydrogen, which is a gas, is a non-metal, what's it doing all the way over there on the left-hand side? Well, there's two reasons. One, this periodic table is arranged in increasing atomic number. And 2, it has metallic-like characteristics, which means it wants to donate that electron. Okay? Metals are electron donors, non-metals are electron receivers. Okay? So this is what we mean by that. See, all of them metals up there are pretty good. They got a whole bunch of like $5 bills in their pocket, or maybe 10. That's probably the going rate now. So some of you guys, you can nod your head yes. Okay? You go to Brookings, maybe Sioux Falls. You maybe ask someone in your class, one of the ladies here, or maybe from Madison or Chester or Flandreau, whatever. So, for a gentleman, who can we pick on? Okay? So, what is in theaters now that you would want to see? Okay? So then, you contact one of the young gals here or someone from another school, whatever. So you're going to go to Brookings to see Jumanji, what, the next level? Is that what it's called? Okay? So, now, when your parents were growing up, and I thought myself included, okay, ladies, how's it supposed to be? Does the gentleman pay for your ticket, the popcorn, and the pop? I agree. I agree. You said all of it. I agree. Okay? Now, okay? So gentlemen, what do you think? Now, okay, so we picked on you because you volunteered. What do you think? Yes. Okay. All right. So someone else over here. Okay. Who can we pick on over here? Okay. What do you think? So, all right. Ladies, who can we pick on for you ladies? Who can we pick on? Okay. Okay. So, it's not what you would expect, but don't you think that would be nice if someone, okay, they pay for your ticket? So you're saying that doesn't happen? Oh, well, okay, well, there's, that can always change. You never know. All right. So my point is, okay, all the guys, they got all these $5 bills in their pockets. So they donate their electrons. Those electrons are like $5 bills. So then all the gals that are in column 7, those are electron acceptors. I know. So they're out there grabbing them $5 bills and just. Okay. So my apologies, ladies. I don't mean to categorize that, but you can ask your parents. I really think that's how they were raised. You go out on a date. The guy pays for the ticket, the popcorn, and the pop, and maybe even the supper, dinner, whatever. I think that's maybe not acceptable. Well, I wouldn't say acceptable. I mean, it's probably not what takes place now, but I think it should. I think it should. Okay, so now going back to this, okay, these will never change. Okay, so someone pick out an element on any element. Okay, so tellurium, element 30. Is it? I don't know. It's on the right-hand side. What element is it? Okay, 52. I was going to say 34. I didn't think that was right. Okay. So tellurium. So what does that? Why did we say 52? Why would we say 52? Because it's the atomic number. So with any element of tellurium, it's always going to have the same number of protons. Okay? The neutrons can vary. We'll get into that at a later time. And the electrons can vary as well, because that's how these form a charge. In element 52, or tellurium, it can form a positive 4 charge, which means it has 4 more protons or 4 more positive charges than electrons or negative charges. Okay, so moving forward. How can you make up a model of something you can't even see? Okay, so the history of why this is important, it's how chemistry has evolved from before Christ all the way up to here. We're talking about Aristotle and Democritus and whatnot. And what we see happening, it's not on a day like today. You're standing outside, okay? And just picture when you were in elementary. Say, I've got dragon breath. Yeah, you're outside. So what happens when you... It's a cold day. That water vapor does what? It freezes so you can see it. That's why you think you got dragon breath. Or maybe it's the guys who just have bad breath. Ladies, is that true? I'm sorry, I don't mean to pick on you. So. Is it true, though? Because some people say, God, they've always got bad breath. So that's why when evaluations roll around, that's why I like to carry these pocket packs, because if a staff member or someone's drinking coffee, you don't want to smell what that coffee is. That's why you'd rather smell peppermint, I think, or spearmint. It smells better than coffee, I'm sure. Okay. So what had happened is the first atom proposed by Dalton here, looked at them as like little tiny spheres. And of course a sphere is just a circle in one dimension, but a sphere is in, 3 dimensions? Right. A circle would be 2 dimensions, I guess. But a sphere is in 3. So it was theorized that these electrons were rotating around that sphere. Now, that's not totally inaccurate. We know now that where do you find electrons? Not on this sphere, but rather what? Rotating around that nucleus. So again, you got to think of, how do you categorize something that you can't see? Okay, and that's what they had come up with. The idea that there's something that's on the surface here that does something that they just don't understand. And that was the first atomic model. Okay? So now, as we move forward, we now know all the way back to, almost 100 years. Okay? It doesn't say when in the 1920s, that we now know that these electrons rotate around the nucleus. And something that you can do, I'm sure everyone has seen the idea of taking Coke or Diet Coke and Mentos. Okay? If you want to do something, and I think it's innocent and silly, is whether you got a Snickers bar, Hershey bar, take a bite of that, then you take your Dr. Pepper, Diet Coke, whatever, and you got that that bite of a chocolate bar in your mouth and you put that soft drink or pop in your mouth, all of a sudden it just balloons up. Why would it do that? What's being given off? It's a chemical reaction, but there must be a gas given off, which it is. Nope. No. Does anyone know what's glucose? C6H12O6. Now, you could say that's the same as maltose. That has C6H12O6. It's the orientation of it that makes it different. But what happens is as you drink that, pop is considered as a what type of beverage? True. Say that again? Oh. No. Carbonated. So what gas must that be given off? No. Someone said it. Carbon dioxide. That's why your mouth balloons up like that. Okay. So what we did last week was what we call the Bohr model. Okay? It illustrates where these electrons are most likely to be found. Now, the reason that that's so important is that establishes all of the different charges on that periodic table. Because you had picked tellurium, which we see element 52 then, okay? That illustrates what charge? A positive. So that must mean there's 4 more positive charges than negative charges. So what has happened is for those electrons, or in this case, $20, 5, 5, 5, and 5, because you said you had all them $5 bills in your pocket. Tellurium was such a nice guy, he gave 4 of those electrons away. 4 of those electrons, each one of them worth $5, so isn't that what it's like at the movie theater? Just yeah. Well, sometimes I think us as a society, if we wouldn't keep sneaking these things in here, well, it's because it's so expensive. Well, the reason it's so expensive is I don't know. That's some of them things you could probably go around and around and around. Okay. So the best thing to do is continually practice these. So probably, I'm not saying a blank sheet of paper, but just somewhere that you can write this, your periodic table, and your slide rule. They had all those those numbers written with a slide on it going diagonally. Any piece of paper, but your table and your slide rule. Okay? So we started with nitrogen, or element number 7. Then I think we did argon. I think we did we do chlorine? Yeah. Fluorine. Okay. Then we did argon. Okay. Now, what I want you to do is pick a number between 21 and 30. Okay? So, when you say we're picking element number 30, that's identifying the element, which is what? Zinc, because it has an atomic number of 30. So how many protons does it have? 30. Okay? So, now we're going to do that Bohr model that has those electron clouds in it. The most likely place you're going to find these electrons. So inside the nucleus, we've got 30, and approximately, 63.59 is that zinc's atomic mass. It's another number written in there. 65.39. Okay, so we're going to say an atomic mass of 65 then. Okay, and this will make more sense tomorrow because this will give us the number of neutrons. All we do is we subtract these two numbers. Okay? So 30 from 65 just gives you what? Okay. Now we're going to start putting those semicircles in there. And to do that, okay, you need your slide rule. Because we really can't make, we can only make one prediction on here. In the D block only, just the D block, what column is zinc in? Okay, so we can make that prediction. That's the only one. So we'll just write that 10 down there because we'll come back to that. Okay, following your slide rule, what energy level are we in to begin with? Okay, so 1, that means first energy level. The first two columns on the periodic table are called which block? The S block, and we're going to put both of them in there. So 1s2, go to the top of the next slide. What does that tell you? We need to put it, and you're right. Why are you right? Because it says 2, that big number 2 says we need to go to the second energy level. What block are we still in? Okay, how many will we put in there? So in other words, all these numbers on the outside should add up to what? It will add up to 30. We're just not there yet. Protons, yes. Okay. So then what comes after 2s2? Okay, so we're still in the second energy level, 1, 2. And we're going to put 6 of them in there from the P block. Now, what does the slide rule tell you to do next? Go to the top. Because you're right. Why do you know that? Because it says 3. So that means we're out of the first, we're out of the second, we're going to the third energy level. And how many electrons? Okay. Keep going down your slide. Okay. Now, do we still go, the element zinc is actually ends in the third energy level. But your slide rule makes a correction for you. What does it tell you? It's telling you to go to the 4s. So that means we're out of the first energy level, we're out of the second energy level, we're out of the third. So what does that big number 4 tell you? We need to add another energy level. And how many electrons would we put in there? Okay? So what comes after 4s2? That's what we said. We're going to end in the third energy level. Okay? So let's look at these numbers. What's 4 times 2? 2, 4, 6, 8. What's 8 plus 12? 20. So now, we take that prediction from before. Zinc is in which column in the D block? 10. So that prediction that we made, and these 20 plus the last 10. How do we get 10 though? It's got 10 columns, and zinc is in which one of those columns? The 10th one. But where do we put that in here? So the third energy level, right here. Okay? When you or anyone goes on to take general chemistry, we really don't want to be talking why you have to do that, but it says because there's different principles we talk about, and some of them are kind of funny to say, where they call it Hund's rule, the Afabu principle. That's really what it's called, Afabu principle. And what that is saying is that these electrons, it's kind of like going downhill. That's why those 10 electrons are going into this energy level, because it takes less energy to fill this one, okay, or excuse me, to fill this one before that one. Now, last thing, then we want to start a little deal. It's called hunting the elements, that explains why the periodic table is arranged the way it is. Okay, when you look at zinc's element box, you see the number 30, you see the number 65.39 or 59 or whatever it is. What else do you see in there besides Zn? Plus 2. So what that is saying, remember we said you guys are so nice because you're going out on this date and you've got to buy popcorn, you got to buy pop and the ticket. So there is 2 electrons on the way outer energy level. That zinc is such a swell guy that he shells out 2 $5 bills to give to chlorine his date, or fluorine his date, or bromine his date. Giving away those electrons. And those halogens out there just grabbing them. And, yeah. My apologies, ladies. That's just the way I've always explained that, because I think it throws a little bit of humor into this. That's the goal of it. We're not meaning to pick on anybody or anything like that. Just all in good fun. Okay, so middle. Are we on the bus? Okay. Right middle. Okay, and some of you are kind of shrugging your heads or saying, and that's okay. We're not being evaluated on this yet. Okay, left outside. Right outside. Right outside. Left middle. Okay, and just keep that in mind. If you're unsure about this, that's okay. This stuff is not easy, okay? But hopefully with a little bit of work, a little explaining, it'll be okay. All right, we'll catch up to you next time.